Okay, I'd like to try number 12 from your problem set. The question is, what is the ratio of electrostatic force to the gravitational force between two electrons? Okay, so the question is comparing two electrons. Now, before we even get started, we have to understand what the question is basically asking. Okay, so you have two electrons, I copied that one, and they are a distance apart that we do not know. We'll call that distance an unknown distance r. It's not known. Okay. And between those two electrons, they will be experiencing some forces. The first force, I think the more obvious one considering we're talking about electrons, is the electric force. Now, because they're both the same particle, they'll both have a negative charge and they'll both repel each other. Equal and opposite like so. So we have the force of electricity repelling equal and opposite. Okay, those vectors are supposed to be the same length. Forgive me if they're not. Okay, let's try to fix it. Yeah, they're about the same. Okay, now the other force that they would be experiencing, because even though electrons don't have a lot of mass, they do have a little bit, they will also experience some gravitational force attracted toward each other, and I'm going to assume that this gravitational force, again equal and opposite, is going to be smaller than the electrical force. And generally we get some sense. I mentioned before, gravity is the weakest of the fundamental forces. That gravity will be weaker than the electrical force. Everything else the same. Okay, so that's the picture that we're looking at. We want to see basically how many times larger, what is the ratio of the electric force compared with the gravitational force. Okay, so let's set that up. So we're trying to find the ratio of the electric force to the gravitational force. And we know when we calculate that out, we will get a unitless number. And the way we know that our final answer will not have units is because, look, we're taking a force, which the units are newtons, dividing it by another force, which the units are newtons. The newtons will cancel out and there will be no units left. So we know our final answer will just be a number saying how many times larger the electrical force is compared with the gravitational force. Okay, so that's basically my conceptual thought process of how I would attack this problem. Now, let's actually start to put the pieces together. Well, we know that the electrical force, the equation, is Coulomb's law. K, the electric constant, times the first charge times the second charge, all over the distance between them squared. And R is unknown, mind you, but we'll just leave that alone for now and see if anything nice happens as we go along. And the gravitational force is very similarly the gravitational constant, big G, times the mass of the first object times the mass of the second object, divided by their distances squared again. And again, those distances are going to be the same for both. Okay, now some nice things happen in that since they're both electrons, the charge is the same. So we can simplify that to say K, Q, charge of an electron, squared. So QE times QE, so 1 and 2 become E, right? So QE squared all over R squared. And similarly, these are both the mass of an electron. Okay, fantastic. All right. We mentioned before we don't know what R is. Now, QE and ME are quantities that are known, and if you don't know them, let's look them up. So I want to write them down. In fact, I'm going to write them down up here, just as a reference. So the charge of an electron, you're responsible for knowing, is 1.6 times 10 to the minus 19 coulombs. The mass of an electron, which I admit I don't remember as easily as the charge of an electron, but anyway, that's 9.109 times 10 to the minus 31 kilograms. Now, true, the charge of the electron is negative. Won't matter here, though, because remember, this electric force and gravitational force, both of these, Coulomb's law and Newton's universal law of gravitation, both give you the magnitude of the forces, so don't worry about the sign. It's squared anyway, so the sign will work out. Don't worry about the sign for this one. Okay, so, but we still don't know the distance between them. In fact, it says just the ratio of the electric force to the gravitational force between two electrons given any radius. Now, the nice thing is the fact that we're dividing the electric force by the gravitational force. So basically, we're dividing every step of the way these two equations. Now, we get to this step here. Okay, so the electric force divided by the gravitational force. It's going to be K QE squared over R squared, all over big G ME squared over R squared also. Now notice something. We have R squared in the bottom in both cases. Now they do cancel out. So you get KQE squared over big G ME squared. And at this point, the ratio of the electric force to the gravitational force is in terms of all things that we know that are given to us. And when I say given, I mean, well, we could look them up. There's no way of knowing how far apart these two electrons are going to be. The problem didn't specify anything about that. But all the rest of these are constants that can be looked up. Okay? So that's the formula, that's the equation that gives us our answer. But now let's actually calculate our number. Okay? So the number that we should get, plug in K, is 9 times 10 to the 9th. I'm not going to put units just for cleanliness here. And then we have the charge 1.6 times 10 to the minus 19. Again, I'm not bothering putting the negative sign. It gets squared anyway. All over big G, which is 6.67 times 10 to the minus 11, all over the mass of the electron, which is 9.109, times 10 to the minus 31. Again, that's also squared, so don't forget your squares that. Okay. So we get approximately 4.2 times 10 to the 42. 10 to the 42. Okay, pretty large there. Now, again, no units because our units completely cancel out because we have a force over a force. This is just a relative number saying that the electric force in this case is 4.2 times 10 to the 42 times stronger than the gravitational force between two electrons. Okay, so that is the final result right there.